Welcome to the Python for Ethical Hackers and Penetration Testing course. I am Bilal Shatti, a cybersecurity engineer and a bug bounty hunter, and today I will be your teacher. In this video, we will talk about what we are going to learn so that you have a clear path about what this course is going to give you. One thing to keep in mind, we have made this course in order to make our students not just some script kiddies that will use pre-built tools without having any knowledge about what is happening in the background. In fact, to be a successful ethical hacker, you need to understand the inner details about computer systems and be able to write your own tools. So in this course, you will learn both coding and ethical hacking. We start by giving you the needed theoretical knowledge about networking, the OSI model, IP, TCP, and ICMP protocols. And we will apply this knowledge by writing our own tools using Python scripting. Some examples of the tools we are going to build are a MAC address changer, network scanner to discover live hosts, and a port scanner to discover open ports. After that, we will dive into details about cryptography, like data hashing, data encryption, and decryption, and we will apply this knowledge by building a password hash cracker in Python. Now let us talk about networking. A computer network is a system of interconnected devices that can communicate with some common standards called protocols. A switch is a network device that can transfer data between devices in the same network. A router is a networking device that links together multiple networks. The Internet is the global system of interconnected computer networks. Now let us talk about MAC and IP addresses. Each device inside the network has two addresses. First, a physical address called Media Access Control or MAC. It is a unique identifier assigned to a network interface controller. Second, a logical address called IP address. It is assigned to the network device once it has connected to a network. Each device inside the network has an out table, which is a list of each IP address and its matching MAC address. Now, how data is exchanged inside the same network, LAN. First, LAN stands for Local Area Network, which is a group of two or more connected computers, and the LAN is a network contained within a small geographic area, usually within the same building. Home Wi-Fi is a common example of LAN. Inside the LAN, devices are connected to each other using a switch, and each device is connected to a given port number of the switch. The switch has a switch table, which is a list of each port number and its MAC address. So if computer 1 wants to send data to computer 2, then the switch will transfer data from port 1 to port 2. In this lesson, we will talk about the OSI model. The OSI model describes 7 layers that devices use to communicate inside the network. Layer 1 is called physical layer. Data in this layer is in the form of bits. In layer 1, cables or Wi-Fi signals will transmit bits from one node to the next node. Layer 2 is called data link layer. It is responsible of delivering messages from one node to the other inside the same network. In this layer, the switch will transfer messages from one NIC to the other using MAC address. Layer 3 is called network layer. It is responsible of delivering messages from one node to the other located in different networks. In this layer, the router will transfer messages from one NIC to the other using IP address. Layer 4 is called transport layer. It is responsible of delivering messages from a process on a source machine to a process on a destination machine. In this layer, messages are delivered using ports. Layer 5 is called session layer. It is responsible of establishing session connection between two hosts. Layer 6 is called presentation layer. It is responsible of defining the method in which the data is to be exchanged between the two communicating entities. Presentation layer services include data encoding, data encryption, and text compression. The last layer is called application layer. This layer, in fact, represents the services that directly support the user applications, like email and file transfer. In this lesson, we will talk about data encapsulation. Step 1. User data starts at application layer. At step 2, when data is passed to the presentation layer, it is encoded or compressed. After that, user data move to the session layer, and now a session ID is attached to the data. At step 4, transport header is appended to the data, including the source port and the destination port. In fact, data plus TCP header is called segment, and data plus UDP header is called datagram. At step 5, IP header is appended to the data, including the source IP address and the destination IP address. Segment plus IP header is called IP packet. At step 6, Ethernet header is appended to the data, including the source MAC address and the destination MAC address. IP packet plus Ethernet header is called Ethernet frame. Last, Ethernet frame is converted into bits and passed through the Ethernet cables or the Wi-Fi signals. The topic of this lesson is to dive into details about how data can be sent from one computer to another inside two different networks. In this scenario, we have computer 1, which is connected to the network 192.168.1.0, that wants to send data to computer 2 in the network 192.168.2.0. To achieve this, we have connected the two computers using two routers, router 1 and router 2. In fact, router 1 can reach computer 1 using its interface ETH0 and can also reach router 2 using its interface ETH1. Router 2 can reach computer 1 using its interface ETH0 and can also reach router 1 using its interface ETH1. Computer 1 and computer 2 are not in the same network, so computer 1 needs to send the frame to its default gateway, which is router 1. Computer 1 sets its own address as the source MAC address and sets router 1 ETH0 interface MAC address as the destination MAC address and then sends the frame to router 1. Router 1 receives the frame from computer 1 on its interface ETH0. Router 1 removes the Ethernet header. Destination IP address is not in the same network as router 1, so router 1 checks its routing table to determine the next hop in order to reach the destination IP address, which is router 2. Router 1 sets its ETH1 MAC address as the source MAC address and sets router 2 MAC address as a destination MAC address and sends the frame to router 2. Router 2 now receives the frame from router 1 on its interface ETH1. Router 2 will first remove the Ethernet header. Destination IP address is in the same network as router 2 and is reachable via its interface ETH0. So router 2 can transfer the frame directly to computer 2. Router 2 sets its ETH0 MAC address as the source MAC address and sets computer 2 MAC address as the destination MAC address and then sends the frame to computer 2. Now computer 2 have received the data from computer 1. Now let us talk about ARP protocol. ARP stands for Address Resolution Protocol. It is used to match an IP address to a MAC address. So if computer 1 at address 192.168.1.5 wants to send data to computer 2 at address 192.168.1.9, first, computer 1 will send to all devices an ARP request. What is the MAC address of 192.168.1.9? Now, all the devices will receive the request, but only the device with the needed IP address will respond. So, computer 2 at address 192.168.1.9 will send his reply, ARP reply. My MAC address is 4FCA3E472E-F1. Now computer 1 will add computer 2 MAC address to its ARP table and now data can be sent between the two computers. Now we will see how we can use ARP protocol to scan a network. ARP scan is a scanning technique to discover live hosts by sending ARP requests to all IP addresses of a given LAN. For example, for the LAN 192.168.1.0, we need to send ARP requests to all of the IP addresses from 1 until 254. If we receive an ARP response from a given IP address, that means the host is live. Now let us talk about man-in-the-middle attack. In this scenario, an attacker will get in the middle of a communication between two devices. First, the attacker will generate a random MAC address and change his MAC address with the new generated one. This is called MAC address spoofing. Second, the attacker will send a spoofed ARP response to the user, saying IP address of the router is associated with the attacker MAC address. Then, the attacker will send another spoofed ARP response to the router, saying IP address of the user is associated with the attacker MAC address. Now, the two devices will update their ARP table, and from this point, they will communicate with the attacker instead of directly with each other. So now, The attacker is secretly in the middle of all communication. Today's topic is Ethernet frame. In fact, in this lesson, we will dive into details about Ethernet frame. First, what is Ethernet frame? In fact, encapsulated data defined by the data link layer is called an Ethernet frame. An Ethernet frame starts with a header called Ethernet header or MAC header. The middle part of the frame is the actual data, and the frame ends with a field called frame check sequence or CRC checksum. The minimum size of an Ethernet frame is 64 bytes and the maximum size is 1518 bytes. Ethernet frame is also called MAC header and is the first 14 bytes of an Ethernet frame. The Ethernet header has three fields. First, the destination MAC address. This is a 6-byte field which contains the MAC address of the receiving device for which the data is sent. In fact, this address is a special MAC address and called broadcast MAC address. And any Ethernet frame with a destination MAC address set to the broadcast will make the frame send to all the nodes inside the same network. Next, the source MAC address. In fact, the 6-byte field contains the MAC address of the sending device from which the data is sent. Next, the type. This 2-byte field contains the type of protocol inside the frame. For example, 0800 indicates IPv4, 86DD indicates IPv6, and 0806 indicates ARP. Now the data section. This area, also called the payload, is where the real data is placed. If IP protocol is used, then both the IP header and data will be placed here. If ARP protocol is used, then data field will contain only the ARP header. The maximum size of data is 1500 bytes, and the minimum size is 46 bytes. If the data length is less than the minimum length, which is 46 bytes, then padding are appended to make up the difference. Last, the CRC checksum. This 4-byte field is called CRC checksum or frame check sequence. The frame check sequence helps the receiver to check the integrity and validity of the frame. Once a frame is received, its checksum is calculated and compared to the checksum field. If both values are the same, then the frame is valid. Otherwise, the frame has been modified in transit and must be dropped. When we want to send an IP packet to a given host inside the same network, first we need to get its MAC address. And to get its MAC address, we need to use the ARP protocol. But what is ARP? ARP is a communication mechanism that is used to translate a logical IP address to a physical MAC address on a local network. And the ARP packet format is used for ARP requests and replies and consists of multiple fields. And the size of the ARP packet is 28 bytes. The first field is the hardware type, which is a 16-bit field that defines the type of the network on which ARP is running, and the value 1 means Ethernet. Next, the protocol type, which is a 16-bit field defining the protocol, and the value 0800 means IPv4. After that, we have the hardware size, which is an 8-bit field defining the length of the physical address in bytes, and the MAC address has a length of 6 bytes. Next, we have the protocol size, which is an 8 bits field defining the length of the logical address in bytes, and IPv4 address has a length of 4 bytes. Next, we have the operation code, which is a 16 bits field defining the type of packet. In fact, type 1 means ARP request and type 2 means ARP reply. After that, we have the sender MAC address, which is a 48 bits field defining the physical address of the sender. Next, we have the sender IP address, which is a 32 bits field defining the logical address of the sender. After that, we have the target MAC address, which is a 48 bits field defining the physical address of the target. Last but not least is the target IP address, which is a 32 bits field defining the logical address of the target. Now let us see an example of an ARP request and reply. In this example, computer 1 at IP address 192.168.152 wants to get the MAC address of computer 2 with the IP address 192.168.1.1. In this case, computer 1 sends an ARP request with the destination MAC address as the broadcast address and the target MAC address all 0 because computer 1 does not know the physical address of computer 2. The destination MAC address is the broadcast address, so the ARP request will be sent to all the nodes in the same network, but only the node with the intended IP address will answer this request. In this case, computer 2 at IP address 192.168.1.1 receives the ARP request from computer 1 at IP address 192.168.152, and computer 2 will send an ARP reply with the destination MAC address as the MAC address of computer 1, the sender MAC address as its own MAC address, and the sender IP address as its own IP address. In this lesson, we will see how we can spoof our MAC address. First, I will show you how to get your current MAC address. We use the command iplink dev, and here we put the name of the network interface. In my case, it is WLP3S0. Link show. So this is my current MAC address. Yours may be different. Now we will change this MAC address. So first thing to do, we generate a new MAC address. Generate a new MAC address. So random MAC is equal to 0x50 0x56. Here I will use the module random 0x0 0x7f. I will copy this. F and here F. Now I will include the module random. Import random. Now Python 3 MAC spoof. I will display it. Random MAC. Each time we run this code, we get a random address. Now, from this list, we will create our MAC address. So, MAC address is equal to, we will join this list by this symbol dot join. We use the function map x. This means show it in hexadecimal. And here the random MAC. Now I will print our MAC address. So this is the random MAC address. I will delete this and new MAC address. I will use this color. Now I will display again. So this is our new MAC address, and each time we run this code we get another MAC address. Now we change the MAC address of our network interface. Step 1, we need to disconnect from the LAN. Disconnect from the LAN. For this we use the command if down and the name of the network interface. So in Python we can use the module subprocess to execute commands. Here subprocess if down, and here my network interface is this. Yours may be different. Now in step 2 we need to deactivate the network interface. IP link set the name of the interface, and here we say down. IP link set the name of the interface and down. Step 3, we change the MAC address, set address, and here we set it to the new random MAC address. So change MAC address, and in step 4 we activate again the MAC address. And this will be up. Step 5, we check the new MAC address. IP link show and here I will display my current MAC address before change. Current old MAC address, old MAC address. So print old MAC address. This will be displayed in red. IP link show WLP3S0. Change the MAC address. Deactivate, then change. Here we activate again the network interface. I will align those commands. And now current, this will be the new MAC address. It will be in cyan. And here the new MAC address. So first thing, we generate a new MAC address. Then we get the old MAC address. Then we will set a new MAC address to our interface. If down, set. This will know my address, not other. Here we enable again. Now we get our new MAC address. Then you need to connect again to the LAN. Let us run this code. Must be, I need to include this. And I close it here. Let us run again this code. So this is the new generated MAC address. This is our old MAC address. Now we are disconnected, and after that we check again our current MAC address, and we see it is equal to the new generated MAC address. If I run IP link show WLP3S0, it is the new MAC address. After this, now we need to connect again to our LAN. In this lesson, we will see how we can use a Python code to discover live hosts in our LAN. First, we import the needed module. For this, we need the module scapy. This module is a third-party module, so we need to install it using pip. Here we will construct the ARP echo request, packets, first Ethernet header, so scapy dot we set here the destination IP, the destination MAC address equals to the broadcast, that means FF broadcast MAC address. Next, we construct the ARP header. ARP is equal to scapy dot ARP. Next, we set the IP address or the LAN subnet that we want to scan. ARP request dot p destination. I will scan my whole LAN /24 print ARP construction complete. I will display it in red. Here we start the scan. Scanning the LAN. For this I will count how much seconds do we need to scan our whole LAN. So I will use the module time. T1 is equal to, here get the current time, T2 or TR scan start, T2 scan complete, time dot time. Here we get again the current time when scan is finished. When scan is finished. When scan is started. I will import the module time. Now we start to scan. Print scan started. I will display it in cyan. Now we use the function SLP to send our packets. Just one thing, ARP request. This is the whole packet. That means the Ethernet header and plus the ARP header. Complete packet. ARP packet. ARP request packet, the Ethernet request, and the ARP. Okay. So we will send this echo requests. The timeout, I will set it to 1 second. That means how many seconds we wait until we receive a response. After that, if we do not receive any response, we can retry using this parameter. I will send only a second one packet if we did not receive any response. I don't want it to be verbose, so this will be false. Here, my network interface, in my case, it is this one. And here I will mention the delay in seconds between the requests. I will set it to 0.00.5. Answer. Now, after the scan is complete, I will print time needed for the scan. That means the difference between T2 and T1. In seconds. The time will be displayed in red. Now we get the live hostess. Send, receive in answer. Print live. Host is received. And here we get the IP address using the parameter psource. Normally, this is all we need. So to summarize, here we are constructing the Ethernet header, and here we use the broadcast MAC address. After that, we construct the ARP header. In our case, we will scan our whole LAN. In this line, we are constructing all the ARP echo request packet. After that, we get the current time before starting the scan. We send the echo requests here using this packet. The timeout, read-write, interface, okay. After that, we get again the current time when the scan is finished. We check how many seconds we need for the scan. After that, we get the responses. Before starting this Python code, we need to be root. So here I changed my user to be root. After that, I will launch this code. Verbosity. Here, verbose. clear. So, in my case, I needed almost 5 seconds to discover how many hosts here in my LAN. In this lesson, we will talk about IP header. An IP header is the bits of information attached to each IP packet that is sent inside the network. The IP header includes address and routing details, which make it possible to reassemble the IP packets and have the original data at the destination address. The size of an IP header is 20 bytes, but when the options field is present in the header size will increase and can reach at maximum 60 bytes. The first header field in an IP packet is the version field. For IPv4, this is always equal to 4, and for IPv6, this is always equal to 6. The size of this field is 4 bits. The second header field in an IP packet is the Internet header length field. The Internet header length field contains the size of the IPv4 header. The length of the header is calculated in the number of 32 bits blocks or 4 bytes blocks. The minimum value for this field is 5, which indicates a length of 20 bytes. The minimum size of the IPv4 header is 20 bytes, and the maximum size of the header including all options is 60 bytes. The size of this field is 4 bits. The third header field in an IP packet is the type of service field. Type of service is used to specify network-relevant service types. Different parameters like bandwidth, the transmission speed, the delay, or the data throughput of the transmission can be defined. The size of this field is 8 bits. The fourth header field in an IP packet is the total length. This field specifies the total length of the packet, including IP header plus IP data. Since a 60 bits field cannot store a value more than 65.53.5, the maximum length of an IP packet can be 65.53.5 bytes, and the size of this field is 16 bits. In this lesson, we will talk about IP fragmentation. IP fragmentation is the process of dividing IP packets into smaller pieces called fragments, so that the resulting pieces can pass through a link with a smaller maximum transmission unit than the original packet size. Identification, flags, and fragment offset fields all deal with IP fragmentation. Now let us see an IP fragmentation example. An IP packet of size 30-20 bytes that must pass through an Ethernet cable of maximum transmission unit of 1500 bytes will be divided into 3 fragments. 2 fragments of size 1500 bytes and another fragment of size 60 bytes. Now let us talk about identification field. This field is used for uniquely identifying the group of fragments of a single IP packet. If an IP packet is too large, then the source host will fragment this packet. All fragments of a given IP packet will have the same identification value. The destination host uses this value to reassemble the original packet from fragments. The size of this field is 60 bits. Now the flags. This 3 bits field is used to control and identify fragments. The first bit is reserved and must be 0. The second bit means don't fragment, and the third bit means more fragment. If the DF flag is set and fragmentation is needed to route the packets, then the packet is dropped. In fact, this can be used to send packets to a destination host that does not have resources to make the reassembly of the fragment. The size of this field is 3 bits. Now, what is fragment offset? This 13 bits field indicates the position of the fragment relative to the beginning of the payload. The fragmentation offset value for the first fragment is always 0. This field size is 13 bytes, so the fragment offset can be from 0 to 8191. And the size of this field is 13 bits. In this lesson, we will talk about the remaining IP header fields. First, TTL. When an IP packet is sent inside the Internet, there is a possibility that this packet will continue to pass from one router to the other indefinitely. To avoid this problem, IP packets are designed with an expiration time called time to leave or hop limit. Each time an IP packet is processed, its TTL value is decreased by 1 second. When TTL value reaches the value 0, then the router will automatically drop the IP packet. The size of this field is 8 bits. Now let us see an example of time to leave. In this example, host A is sending an IP packet to host B. First, host A sends an IP packet with a TTL value of 255. Second, router 1 receives the IP packet, decreases the TTL value by 1, and sends the IP packet to router 2, but now with a TTL value of 254 instead of 255. After that, router 2 receives the IP packet, decreases the TTL value by 1, and sends the IP packet to router 3, but with a TTL value of 253. Last, router 3 receives the IP packet, decreases the TTL value by 1, and sends the IP packet to host B, but with a TTL value of 252. Next, the protocol field. In fact, this field defines the protocol used in the data portion of the IP segment. For example, 1 means ICMP, 6 means TCP, and 17 means UDP. And the size of this field is also 8 bits. Now the header checksum. In fact, this field is used to check the errors of the IP header. In fact, when an IP packet arrives at a router, the router will calculate the checksum of the IP header and make a comparison to the checksum field. If the values do not match, then the router will discard the IP packet. The size of the header checksum field is 16 bits. Now we will talk about the source IP address, destination IP address, options, and padding. First, source IP address. In this field, we have the IPv4 address of the sending device, and the size of this field is 32 bits. For the destination IP address, here we have the IPv4 of the receiving device, and the size of this field is also 32 bits. Last, options and padding. In this field, we have the IPv4 options. In fact, the size of this field is a multiple of 32 bits. And if an option is not 32 bits in length, then it uses padding options in the remaining bits to make the header an integral number of 4-byte blocks. In this lesson, we will talk about ICMP protocol. ICMP, or Internet Control Message Protocol, is a network protocol that is used to diagnose network communication issues between networking devices. Common examples of ICMP are discovering if a host is live or not using ICMP echo request and ICMP echo reply messages, trace routing an IP packet using time-exceeded TTL expired messages. Now, let us see an example of ICMP live host discovery. In this example, host A wants to check if host B is live or not. So, host A sent an ICMP echo request packet to host B. And if host B is live, it will send an ICMP echo reply packet to host A. Now, let us see an example of ICMP address trace routing. First, host A sends an ICMP echo request to host B with a TTL value of 1. Step 2. Router 1 receives the ICMP echo request, decrease the TTL value by 1. Now TTL value is equal to 0. So router 1 drop the packet and send an ICMP TTL expired to host A. Now host A discovered the IP address of the first router in the path to host B. Step 3. Host A sends an ICMP request to host B, but now with a TTL value of 2 instead of 1. Step 4. Router 1 receives the ICMP echo request, decrease the TTL value by 1. So now TTL value is equal to 1 instead of 2. TTL value is greater than 0, so router 1 do not drop the packet, but instead will transfer the packet to router 2. Step 5. Router 2 receives the ICMP echo request, decrease the TTL value by 1. TTL value is equal to 0, so router 2 drop the packet and sends an ICMP TTL expired to host A. At this step, host A has discovered also the second router in the path to host B. Step 6. Host A sends an ICMP request to host B with a TTL value of 3 instead of 2. Step 7. Router 1 receives the ICMP echo request, decrease the TTL value by 1, so now TTL value is equal to 2. TTL value is greater than 0, that means router 1 will transfer the packet to router 2. Step 7. Router 2 receives the ICMP echo request, decrease the TTL value by 1, and now the TTL value is equal to 1. TTL value is always greater than 0, so router 2 will transfer the packet to host B. Step 8. If host B is live, then it will send an ICMP echo reply packet to host A. And now, host A have discovered all the paths to host B. In this lesson, we will talk about the ICMP header. The ICMP header starts after the IPv4 header. All ICMP packets have an 8-byte header and a variable-sized data section. Type and code fields. The size of each field is 8 bits. The type field combined with the code field indicate the ICMP type of the packet. The checksum. The ICMP checksum is a 16-bit value that is computed from the ICMP header and the payload and is used to verify the integrity and validity of the ICMP message. When calculating the checksum should be set to 0. The identifier is set in the request packet and echoed back in the reply to be able to keep different ping requests and replies together. The sequence number usually starts at 1 and is incremented by 1 for each packet. Last, the data section. When sending an ICMP echo request, we can send some data in the payload section. For example, we want to exfiltrate data from the machine we are attacking, and external HTTP requests are not allowed by a certain firewall, but external ICMP requests are allowed. In this case, we can exfiltrate data from the victim machine to our machine using an ICMP echo request. ICMP error messages contain a data section that includes a copy of the entire IPv4 header, plus at least the first 8 bytes of data from the IPv4 packet that caused the error message. Here are the most common ICMP messages. Type 8 and Type 0 are for echo request and echo reply. In fact, those two messages are used to discover if a given host is live or not. Type 11 indicates that TTL has been expired during transit or during reassembly of the packet fragments, and Type 3 indicates destination are reachable. In fact, destination can be a network, a host, a protocol, or a port number. Now that we have understood the basics of IP trace routing techniques, it is time to write a Python script that will achieve this attack. First, we will start by adding the module argparse. In fact, we need this module to add our options to our Python script. First is the parser. Here in the description we have put IP trace routing Python script. Now we start by adding the options. The first option is the IP address. This is the IP address that we want to IP trace route. And here the maximum hop limit. we want its type to be integer, so int, and in the help, maximum hop limit. Now we get the arguments. Here we get the target IP address, and here we get the maximum hop limit. For the moment, I will just display those two values. So we import the module argparse. Here the description of the Python script. Here we add the arguments, and here we get the arguments. So if I run the script, IP trace route, here the help options. Now, if I specify an IP address and a maximum hop limit of 10, for example, okay, as we can see, we are getting those two values from the terminal. The next step is to validate the IP address. In fact, we need to make sure that the target IP address is a real IP address. For example, if I type here random string, it will just take it as input. So we need to resolve this issue. For this, I will use the module IP address. So here we have defined a new function called isValidIP that will take an IP address and check if it is a real IP address or not. So now we are taking our target IP address and we check if it is valid or not. Now let us try this. If I type here, so here it will tell us that it is invalid IP address. And if we type an IP address like this, we will have no error. I will remove this line because we don't need it. The last step in our code is the IP trace routing logic. First, we will initialize a TTL value by 1. TTL initialization. Here we display a message called IP trace routing start. I will get the time of starting the IP trace route and I will call it T1, which is equal to time. So we need to add the module time. Now we start to send our ICMP packets inside a while loop. First, we construct an ICMP packet. To construct the ICMP packet, we need to use the module scapy. So we need first to include it in our Python script. Next, we need to send this ICMP packet. We will wait for 3 seconds at maximum for a given response. So timeout is equal to 3. In case we don't get any response, we will send again another ICMP packet. So retry equal 1. And I don't want it to be verbose. So verbose equal to false. Here we send the ICMP packet. And here we construct the ICMP packet, which equal to IP header plus ICMP header. In case we get a valid response. And here, if we don't get any response, else. So if this instance, okay, when we get a response, that means it may be an ICMP TTL expired or ICMP echo reply. Let us start with the ICMP TTL expired. So if the IP header, the ICMP header is of type 11 and the code equals 0, that means it is ICMP TTL expired. In this case, we will print the IP address of the router. We will print also the TTL. I will display it here in cyan. We need also to increment the TTL value by 1. Now if it is an ICMP echo reply, in this case, we have reached the target IP address. Target IP address. And we don't need to increment the TTL value. So if it has the type now if we don't get any response, a known router and the TTL that we have used, now we get again the time after the IP trace routing has been finished, and we will print how many seconds has been taken to get this done. IP trace routing done in T2 minus T1 seconds. Let us check our code. First, we initialize the TTL value by 1. We get the time of the start of the IP trace routing. Now, inside the while loop, we construct our ICMP packet. Next, start sending the ICMP packets. So if we have a response, type no equal to false. In case it is ICMP TTL expired, that means the type is 11 and the code is 0. Here we get the IP address of the router that we have discovered. We increment the TTL value by 1. In case it is ICMP echo reply, that means we have reached the target IP address. So the type is 0. Here we display the target IP address and we don't need to increment the TTL, but we need to exit the loop. In case we don't get any response, we simply display a known router, and here the TTL, and we also increment the TTL by 1. After that, we get the time again, and here we display the message IP trace routing done in T2 minus T1 seconds. Okay, let us try this code. First thing, we need to be root in order to start this Python script. I am already root. Now, if I run the script, I will choose this IP address as an example, and the maximum hop limit is 10. So this is the first router in our pathway. After that, we have this IP address and so on until we reach this IP address. For example, when we have a TTL value of 5, we did not receive any response. Let us run again this code and see if we can get the IP address when the TTL is equal to 5. I think there is some type of firewalls that is blocking this ICMP packets. Here the time of the scan is almost 7 seconds. The topic of this lesson is to dive into details of the TCP protocol. In fact, when a computer wants to communicate with another computer, the communication between those two devices must be reliable to guarantee that all data is received in order. Let us consider this scenario. In this scenario, computer 2 is downloading a file from computer 1 using unreliable transport protocol like UDP. After sending all data, computer 2 may get an incomplete file with data not in order. In this example, the received file is of a complete file. This is an example, so as you can see, the file is incomplete and data not in order. Now, let us consider the second scenario. In this scenario, computer 2 is downloading a file from computer 1 using a reliable transport protocol like TCP. In fact, after sending all data, Computer 2 will get a complete file with all data in order, and the received file in this case is this is an example of a complete file with data in order. But what is TCP? The Transmission Control Protocol, or TCP, is the most common transport layer protocol. In fact, TCP provides multiple services to the application layer, including connection-oriented service and reliability. In fact, before starting exchanging data, connection must be first established between end systems. After that, data can be transferred, and after exchanging all the data, the connection must be closed. Second, reliability. In fact, TCP includes methods like sequence number, acknowledgement number, and checksum to solve many of the problems, such as lost packets, out-of-order packets, duplicate packets, and corrupted packets. In this lesson, we will talk about the TCP three-way handshake. In fact, before TCP starts to transmit data, connection must be first established between end systems. This TCP connection is called TCP three-way handshake. Let us consider this example. In this example, a client is requesting a web page from a web server. Step 1. The client will send a TCP SYN packet. That means it is a synchronization request to open a connection with the server. Step 2. The server will respond with a TCP SYN ACK packet, means server acknowledges the client synchronization request. Step 3. The client will send a TCP ACK packet. It is an acknowledgement response saying we can now start communication. After establishing the connection, data can now be exchanged using TCP push ACK packets. After finishing exchanging all the needed data, connection must be closed. So the client will send a TCP FIN ACK packet, which is a request to close the connection. And at step 2, the server will respond with a TCP FIN ACK packet, means server acknowledges the client closing connection request. Finally, the client will send a TCP ACK packet. That means it is an acknowledgement response saying we can now close the connection. Today's topic is port scanning techniques. In fact, transport protocols like TCP and UDP specify the source and destination port numbers in their packet headers, and that information, along with the source and destination IP addresses and the transport protocol, enables the communication between applications. The combination of an IP address and a port number is called a socket, and the port is a 16-bit number used to identify specific applications and services. So a port number is in the range of 0 and 65535, and port numbers in the range from 0 to 1023 are the well-known ports or system ports. Now let us see some examples of port numbers. Port 80 used for requesting web pages using plaintext HTTP protocol. Port 443 used for requesting web pages using encrypted HTTP protocol called HTTPS. Port 21 used for requesting files using FTP protocol. and port 22 used for sending encrypted shell commands using SSH protocol, and port 25 used for requesting emails using SMTP protocol. Applications that provide a service will open a port on the hosting computer and listen for connection requests. A client can request the service by sending the request to the application IP address and port. Let us see an example. In this example, a server is providing HTTPS web pages and SSH secure shell services. The server has multiple services like SSH, FTP, SMTP, HTTP, and HTTPS, but the server administrator decided to enable only HTTPS and SSH services. To achieve this, the server administrator will close all the ports and open only the port 443 used by HTTPS and the port 22 used by SSH. If the client requests some data from the server, it will first send a TCP SYN packet to the server. If the port is closed, the server will respond with a TCP RST packet, meaning connection cannot be established and the requested service is unavailable. And if the port is open, the server in that case will respond with a TCP SYN-ACK packet, meaning connection can be established to start data exchange with the requested service. In case the client requests the web page using plaintext HTTP protocol, it will receive a TCP RST packet because port 80 is closed. And in case the client requests the web page using encrypted HTTPS protocol, in that case it will receive a TCP SYN-ACK packet because port 443 is open. In this lesson, we will dive into details about port scanning techniques. Port scanning is the process of scanning a target computer to identify open ports. Common port scanning techniques include TCP Connect Scan. This is the most basic and straightforward technique. It attempts to establish a full TCP connection with the target by sending a SYN packet and waiting for a SYN-ACK response. If the port is closed, it will respond with an RST packet indicating the port is closed. And if the port is open, it will respond with a SYN-ACK packet indicating the port is open. In this case, the attacker must send back a TCP-ACK packet to establish the full TCP connection. The next port scanning technique is the TCP SYN scan or half-open scan. This technique is similar to the TCP Connect scan, but instead of completing the three-way handshake, it sends only a SYN packet. The advantage of this technique is that it does not establish a full connection, reducing the chance of detection by an intrusion detection system. If the port is closed, it will respond with an RST packet, indicating the port is closed. And if the port is open, it will respond with a SYN-ACK, indicating the port is open. The next scanning technique is the TCP FIN scan. This method involves sending a FIN packet to the target port. If the port is closed and not filtered, it will respond with an RST packet indicating the port is closed. And if the port is open and not filtered, it will not respond at all, indicating the port is open or filtered. The last case is the port is open and filtered. In this case, the firewall will drop the packet before reaching the port and no response is sent back to the attacker. But some firewalls can forge a RST packet and send it back to the attacker to indicate that the port is closed, but in reality the port is open. The last technique is the TCP ACK scan. An ACK scan, also known as an Advanced Port Scan or TCP ACK scan. Unlike other port scanning methods, the ACK scan does not directly determine whether a port is open or closed. Instead, it focuses on examining the response behavior of the target system to check if a port is filtered or not. An unfiltered closed port always responds with an RST packet when it receives an ACK packet, and an unfiltered open port always responds with an RST packet when it receives an ACK packet. And in case the port is filtered, it will not respond when it receives the ACK packet, or it will send back an ICMP error message. But some firewalls can forge a RST packet and send it back to the attacker to indicate that the port is unfiltered, but in reality the port is filtered. In this lesson, we will dive into details about the TCP segment header. In fact, a TCP segment consists of a segment header and a data section. The TCP segment header contains 10 mandatory fields and an optional field called options. The minimum size of the TCP header is 20 bytes if options field is not present, and its maximum size is 60 bytes. The data section follows the TCP header is called the TCP payload, and the length of the data section is not specified in the TCP segment header, but it can be calculated using the below rule. Data length is equal to the total IP packet length minus IP header length plus the TCP header length. And in fact, the total IP packet length is specified in the IP header. The first field in the TCP header is the source port. This field of size 16 bits represents the port number of the sender application. Next, the destination port. This field of size 16 bits indicates the port number of the receiver application. After that, we have the sequence number. This field specifies the sequence number of the first data byte in the TCP segment. It is used for data ordering and flow control. We have also the acknowledgement number. In fact, if the ACK flag is set, this 32 bits field contains the next sequence number that the sender of the segment is expecting to receive. It acknowledges the receipt of the previous data. After the acknowledgement number, we have the data offset. This 4 bits field specifies the length of the TCP header in 32 bits words. We have also reserved field. In fact, these 6 bits are reserved for future use and should be set to 0. We have also the control flags. The first bit is called the urgent flag. It indicates if the urgent pointer field is significant. When this bit is set, the data should be treated as priority over other data. Next, we have acknowledgement flag. It indicates if the acknowledgement number field is significant. Next, we have the push flag. In fact, it requests the receiving TCP to push the received data to the application immediately. After that, we have the RSC flag, which means close immediately the connection. Next, we have the synchronize flag. It synchronizes the sequence numbers to initiate a connection. Finally, we have the fin flag. It indicates to the receiver that the sender wants to terminate the connection. The next field is the window size. In fact, this field specifies the size of the receive window, which is the amount of data that the sender can transmit before receiving an acknowledgement. Using this field, TCP client or server can advertise a maximum of 64 kilobytes as its buffer size to the other end user. The next field is the checksum field. In fact, the 16 bits field is used for error detection of the TCP header and data. It covers both the TCP header and payload. Next, we have the urgent pointer, which is a 16-bit field that is an offset from the sequence number indicating the last urgent data byte. In fact, this field is considered valid and evaluated only if the urgent bit is set to 1. Finally, we have options and padding. This field is used to include additional TCP options such as maximum segment size, window scaling, and timestamps. First, what is the maximum segment size, or MSS? It is the largest amount of data specified in bytes that TCP is willing to receive in a single segment. For best performance, the MSS should be set small enough to avoid IP fragmentation, which can lead to packet loss and excessive transmissions. To accomplish this, typically the MSS is announced by each side using the MSS option when the TCP connection is established. The MSS is derived from the maximum transmission unit (MTU) size of the data link layer of the networks to which the sender and the receiver are directly attached. In fact, MSS is equal to MTU minus the TCP header plus the IP header. And MTU is the largest packet or frame size specified in octets, 8-bit bytes that can be sent in a packet or frame-based network. The common value of MTU on the internet is 1500 bytes. We have also the TCP window scaling option. This feature allows the use of large window greater than 64 kilobyte on a TCP connection. Window size field in the TCP header limits the window size to 64 kilobyte. If larger windows are desired, applications can increase the size of their socket buffers, and the window scaling option will be employed. In fact, new window size is equal to window size multiplied by 2 to the power of the scaling factor. In fact, during TCP handshake, the client sent a SYN packet with window size equal to 64 kilobytes, and in the options field, it specifies a scaling factor of 7. In this case, the client will allocate a TCP buffer with a size equal to 64 multiplied by 128, which is equal to 8 megabytes. Now that we have understood the basics of the TCP protocol and the types of the port scan, it is time to write a Python script that will achieve port scanning techniques. First, let us start by adding the needed arguments for our Python script. For this, we will use the module argparse. Now we get the arguments from the command line. First argument is the network interface. Next is the target IP address. After that, we have the ports to be scanned. Last is the type of the scan. Port scanning techniques include scene scan, XScan, FinScan, XMass scan, and TCP connect scan. Now we get those options. Network interface, after that target IP address, now the scan ports, and last the scan type. Now we will display all these options. Let us run this code. If you run the help option, we get all the arguments that we need. Now let us take as an example this network interface, this IP address, those two ports, and the scan type as scene scan. So as you can see, we have get those options from the terminal and they are displayed here. The next step is to validate those options. We start with the IP address. So validating target IP address. We need to make sure that this is a real IP address. For this, we will use the module IP address. Next, we define a function called isValidIP. So here we are checking if this is a real IP address or not. In this case, we are returning true. And if it is not a real IP address, we will return false. Now we check if is valid IP, the target IP address is equal to false. In this case, we print an error message and we exit. Error invalid IP address. So here we are using a new function called isValidIP. If it is a real IP address, it will return true, otherwise it will return false. After that, we use it to check the target IP address. Now let us run this code. Python 3 port scan my network interface. I will put random here 21 and scene scan. So here we are getting an invalid IP address. Now if I type, for example, a valid IP address, now we don't get any error. Next, we validate the ports that we will scan. Now, validating ports. So scan port range 1 is equal to scan port dot split. For example, if scan port is equal to 21, 22, 80, that means scan port range 1 is equal to 21, 22, 80. So we are constructing a list from the string scan ports. We will use another list, range 2, and for the moment we will keep it empty. So for element in scan ports range 1, try element is equal to int element. Here we are converting the string element to an integer. Convert to integer. Next we check if element is between 0 and 65, 535. Valid port. In this case, we add this element to this list. Scan ports, range 2, append element. Otherwise, it is not a valid port. Invalid port number. And we exit. And here accept invalid port number. Port number must be between 0 and 65535. And we exit also here. Now let us check this. We don't get any issue. For example, if I type this, in this case we get port number must be between 0 and 65535. VM port scan. I will display it in red. And now I will print scan ports range 2. If I change it to a valid port number, okay. Now we validate the scanning technique. Validating scan type. So if scan type not in this list, scene scan ACK scan fin scan xmas scan fin scan xmas scans TCP connect scan. In this case we will print invalid scanning technique. And we exit. So this is okay. If I write also okay. If I write random scan, for example, in this case you will get the message invalid scanning technique and the Python script will exit the execution. Now let us move on to our scanning techniques. The first scan will be scene scan. For this, we will define the function called sceneScan. Def sceneScan. As options for this function, we will need the network interface, the target IP address, and the target port. First, we construct a scene packet. For this, we need the module SCAPI. So scene packet is equal to SCAPI dot IP. Destination will be the target IP address, and for the TCP header, destination port will be the port, and the flags will be S for sceneScan. So first thing, we need to import the SCAPI module. So SCAPI.IP destination, SCAPI.TCP destination port, and the flags. Next, we send the scene packet using the function SR1. We'll set the timeout for 1 second. We don't want it to be verbose. And here the network interface. So if the response has layer TCP, first we check if it is a scene ACK. That means port is open. Now we print port closed. If we don't get any response, that means port is filtered. This is an empty line. So let us check. First, we construct the packet. Here, network interface, the target IP address, the target port. First, we construct the SIM packet, target IP address, target port. Flags is equal to S, that means SIM packet. Then we send the SIM packet. If we get a response and the response has a TCP layer, first we check if it is a SYN ACK packet, that means the port is open, and if it is an RST ACK packet or RST packet, that means the port is closed. And if we don't get any response, that means the port is filtered. Now, if scan type is equal to SYN scan, we will print starting SYN scan and for index scan port in enumerate scan ports range 2. Here we are getting all the ports one by one. We call now the function SYN_SCAN with the argument network interface target IP address and the scan port. So if scan type is equal to SYN_SCAN, we print this message. Then for index scan port in enumerate scan ports range 2, we call the function SYN_SCAN with the parameters network interface. After that, we have the target IP address and the scan port. Let us try this code. I will use this Python script to scan scanme.nmap.org. First, I will get its IP address using dig command. So this is our IP address that we will scan. Now, Python 3. First, we need to be root. I am already root. Now we start the scan, port scan. The target is 45, 33, 32, 156. My network interface is this one. I will scan those ports. And here the IP, target IP address, and here the type of the scan. TCP is not defined. VM, port scan, scapy.tcp, scapy.tcp, let us run again the code. Port is not defined. Print target port. Port. Okay, here we get the response. In our case, the port 21 is closed, port 22 is open, 25 is closed, 80 is open, and 443 is closed. The next type of scan will be ACK-scan. First, I will copy this function. This will be ACK-scan at ACK packet construction. This will be ACK packet. Instead of SYN flag, this will be the ACK flag. Next, we send the ACK packet. After that, we check if we have a response. If response has TCP layer, I don't need this line. We check if it is RST ACK or RST packet. That means the port is unfiltered. This will be unfiltered. Otherwise, the port is filtered. Let us check. This is the ACK-scan function, ACK-scan packet. Here we send the ACK packet. We check if the response is a TCP packet. Then we check if it is RST ACK or RST packet. That means the port is unfiltered. Otherwise, the port is filtered. I will remove this line. I don't need it. Now I will copy this block of code. ACK-scan, starting ACK-scan, and here ACK-scan. Okay, just one check. ACK-scan, starting ACK-scan. Okay, now let us run this code. First, I will get the IP address of scanme.nmap.org using dig command. class answer scanme.nmap.org. Now Python 3 port scan. The network interface will be this. This is the IP address. The ports that we want to scan: 21, 22, 25, 80, 80, 80, and 443. And the type of the scan will be type of the scan, which option? S ACK scan. So all of those ports are infiltrated. Now let us check if they are open or not using the CD scan. So we have port 22 open and port 80 open. After implementing the ACK scan, it is now time to implement the fin scan. I will start by copying this code. So this will be fin scan, fin packet construction. This will be fin packet, and instead of ACK flag, this will be the F flag. Next, we send the fin packet. Here will be fin packet. So if it is a TCP response and the response has the RST ACK flag or RST flag, that means the port is closed. Here will be closed. Otherwise, the port will be open or filtered by a firewall. Just one check: fin scan, fin packet, the fin flag, send the fin packet. If it is a TCP response with RST or RST ACK packet, it is closed. Otherwise, the port is open or filtered. Now I will copy this. Here will be fin scan, fin scan. After that, we display the message starting fin scan, and here we call the function fin scan. Let us run this code. Fin scan. Just one thing, I will display this port in cyan, and for the ACK scan, this also must be in cyan, not in the red color. Cyan and red. Okay. So port 21 open filtered, 22, 25. So according to the fin scan, all of those ports are open filtered. After the fin scan, we have the XMAS scan. I will copy the fin scan code and this will be XMAS. An XMAS packet is a TCP packet that has the fin flag, the push flag, and the urgent flag enabled. So that means we need to change only this flag to, instead of F, to FPU. I will change the name of the packet from fin to xmas, and here xmas packet. Now I will copy this and this will be xmas scan. We display the message xmas scan started, and then we call the function xmas scan. Just one check. We have enabled the fin push and urgent flag. We change the name of the packet to xmas packet, and here the same logic as the fin scan. Now let us run this code. I am root. I will get the IP address of scanme.nmap.org plus no all plus answer. Now I will call the port scan script, port scan. My network interface is this. I want to use the xmas scan. The target IP address is 45.33.32.156, and I want to scan the port 21, 22, 25, 80, 80, 80, 443, and 53. Let us run this code. Start an xmas scan. So according to the xmas scan, all of those ports are open or filtered. If we run the fin scan, normally we get the same results. And if I run the xscan, in the xscan we see that all of the ports are unfiltered. And if we run the scene scan, some ports are open and others are closed. Now let us make some conclusions. We use the scene scan to confirm that a given port is open. In our case, those two ports are confirmed to be open. Now for the remaining ports that are closed. Here we need to check if those ports are really closed or filtered. So we run the xscan. In the xscan it is unfiltered. So that means those ports are not filtered by any firewall. And in the fin scan, we see that the results of those ports, all of them are open or filtered. That means we did not receive back any response. There is a high probability that those ports are filtered. Here also we have the same results. So as a conclusion, there is a big possibility that those ports are really filtered, and the firewall is sending back an XT packet when we make the xscan. That's why we have this as unfiltered. The last type of scan will be TCP connect scan. Def TCP connect scan. In this scan, we will establish a full TCP connection with a given port. Here, the destination IP, and the other parameter will be destination port. I will construct a TCP socket. I will call it client socket, and I will use the module socket. Socket.socket, socket.af inet, and socket.sock stream. This line means construct a TCP socket. Construct a TCP socket. Now we try to establish a full connection, establish a full TCP connection with the port that we want to scan. Client socket.connect, we use the function connect. Here we get the destination IP and the destination port. So if we get the TCP connection to be established, that means the port is open. Print port is open, destination port, destination port open. I will display it in cyan. After that, we close the connection. Client socket close. Close the connection, and here connect to the port and establish a full TCP handshake. Otherwise, we get an exception. In this case, the port is closed. And we print destination port. This will be in red, closed. First, I will call the socket module, import socket. Then I will add the block of code for the TCP connect scan. This will be TCP connect scan. Starting TCP connect scan. This will be the function TCP connect scan. I don't need the network interface. This is the IP address and this is the port. Let us check our code. In fact, we don't need those semicolons. This is not C language or PHP. I will remove them. So the client socket, socket.socket, socket AFINet, sockstream. We try to establish the full TCP connection using the function connect. If the connection was successful, that means the port is open, and after that we close the connection. Otherwise, the port is closed and we display the message port is closed. Now let us try this code. Python 3, port scan, my network interface, target IP address 45.33.32.156. After that, the type of the scan. In my case, this will be TCP connect scan, and the ports that I want to scan will be 21, 22, 25, 80, 80, 80, 443, 53, and 67. So according to this scan, we have only the port 22 and the port 80 as open, and the remaining ports are closed. In this lesson, we will dive into details about the shell command line interface. But first, what is a shell? A shell in the context of computer science and operating systems refers to a user interface that allows users to interact with an operating system and execute commands. The shell acts as an intermediary between the user and the underlying operating system, providing a way to execute programs, manage files, and perform various system operations. A shell provides a command line interface where users can enter text-based commands to perform specific tasks. The shell executes these commands by invoking the needed system utilities. Examples of popular shells include Windows PowerShell, Windows Command Prompt, Unix Bash, Unix Z Shell, and Unix C Shell. Now let us see some examples of Linux Bash commands. In fact, in Linux operating systems like Ubuntu and Debian, the default shell is Bash. To get the hostname of the current machine, we can simply use the command hostname. To write a message to a file, we can simply issue the command echo our message file name. To get the contents of a file, we use the command cat file name. And to encode the contents of a file, we use the command xxd file name. Now that you have understand the basics of the shell, it is time to dive into details about the bind shell and the reverse shell. First, what is a bind shell? A bind shell refers to a type of shell that binds to a specific network port on the target machine and waits for incoming connection. Once a connection is established, the bind shell allows the remote attacker to interact with the target system by providing them with command execution capabilities on the compromised machine. But what is the bind shell steps? First, the attacker exploits a vulnerability on the target system, like command injection, that binds the bash shell to a network port and start listening for incoming connections. Step 2. The attacker connects to the predefined port on the victim machine and gains control over the shell session. Step 3. The attacker starts executing the shell commands on the victim machine. In some scenarios, The victim machine is protected by a firewall, blocking incoming connections. In this situation, the attacker is not able anymore to connect to the victim machine, so bind shell is not possible. To bypass this, we can use a reverse shell instead of a bind shell. But what is a reverse shell? A reverse shell, on the other hand, establishes a connection from the victim machine to the attacker machine. In this scenario, the target machine initiates the connection and connects to the attacker machine. But what are the steps of the reverse shell? First, the attacker starts listening for incoming connection. Step 2, the victim connects to the predefined port on the attacker machine. Step 3, once the connection is established, the attacker gains control over the target system through a shell session. Last, the attacker starts executing the shell commands on the victim machine. Now that you have understood the basics of the bind shell, it is time to write our bind shell using Python code. I will use my current machine as the attacker machine, and I will use this virtual machine as a victim machine. First, we start by importing the socket module. Import socket. After that, we create a TCP socket, socket.socket. Here we use the option if inet, and the other option is sock stream. These lines mean create TCP socket. After that, we bind the socket to an IP address and a port number. So s.bind the IP address. This is the IP address of the victim machine. And I will listen to this port. Now we start listening for incoming connection. Use the function listen for incoming connection. And once a connection is made, we need to accept it. So accept incoming connections. For this, we use the function accept. And once a connection is accepted, we need to create another socket for the new client. We will call it shell socket. The next step is to redirect user input, the output, and the errors to the socket. So we use the module OS and the function dap2. Our socket is called shell socket. We need to get its file number, and here 0. 0 means standard input, which is also called stdin. I will copy this I will replace this by 1 and this by 2. Replace this by 1 and this by 2. 1 means output. In fact, 0 means input, 1 means output, and 2 means errors, which is also called std errors and std out. I will include the module OS. After that, we need to execute the bin bash shell using sub process. So sub process dot call bin bash, and we will use the option I need to import also this module sub process. Let us check our code. First, we create a TCP socket and we bind this socket to an IP address and a port number. After that, we listen for star for incoming connection. And once a client has connected to this bind shell, we need to accept this connection. And for this, another socket is created to handle this client. After that, we need to redirect std in, std out, and std error for the shell socket. And after that, we need to execute the bin bash shell using subprocess. Now, from the victim machine, I will start this bind shell. And from my machine, I will connect to this shell. This is the IP address of the victim machine, and it is listed on this port, so we need to use also this port. So as we see, we have received now the bind shell. Just one thing, in this machine, this is the current user, this is its IP address, I will run this command to show you that you have the same results. This is the user of the victim machine, this is its IP address, this is the current directory, and this is its contents. So as we see, like this, we have connected to the victim machine and we have received a bind shell from it. In case there is a firewall that it is protecting the victim machine from external attacks, in this case, the attacker will not be able to connect to the victim machine. So to resolve this issue, we need to make the client connect back to our attacking machine. First, I will start listening for incoming connection. For this, I will use the tool netcat. I will listen on this port. N means numeric, L means listen, V for verbosity, and K means keep alive, and P for the port number, and S to specify the IP address. I will put this, that means listen to any IP address. After that, instead of using the bind shell, we will use something called reverse shell. So bind shell, instead we will use the reverse shell. Then The only piece of code that we need to change is those 3 lines. Instead of listening for incoming connections, we will connect to the attacker machine. So I will connect. My attacker machine has this as an IP address. I am listening on this port. So this will be the port that we need to use. Now, if I run this code, shell socket, I will call this shell socket, and this is shell socket. Because here the name of the socket is shell socket, and it must be the same. So now I have connected to the attacker machine. If I come back here, as you have seen, here we have received a reverse shell from the victim machine. So who am I? It is dust. What's this directory? What's the content of this directory? And so on. So as we see, we have received a reverse shell from the victim machine, and now we are able to execute commands on the victim machine. Now let us talk about data encoding. Encoding is the process of converting the data into a specified format like base 64 and hexadecimal. Decoding is the reverse process of encoding, which is to get information from the converted format. Data hashing. A hash function is a mathematical function that converts an input value into another compressed value called digest. A hash function is one way we cannot get the original data from a given digest. It is also of a fixed size. That means the input to the hash function is of a random length, but output is always of a fixed length. It is unique. That means two different input data cannot have the same output digest. Different hashing functions exist, like MD5 and SHA-256. But why do we need data hashing? Hashing is used for password protection and data integrity check. In fact, instead of storing the plaintext password, we will store its hash in the database. So if some bad actors get access to the database, they will find only hashes and not the plaintext passwords. Data integrity. If one bit of data has been changed in a given message or file, then its digest will also change. So if you compare two hashes generated at different moments of the same data, and you find that the hashes are not the same, that means data has been modified. In this lesson, we will talk about data encryption. Encryption is the process of securely encoding data in such a way that only authorized users with a key or password can decrypt the data to reveal the original. Data returned by encryption is called ciphertext, and data returned by decryption is called plaintext. Two algorithm types of encryption exist: symmetric encryption and asymmetric encryption. But why do we need data encryption? Let us imagine this scenario. Alice wants to send a message to Bob, but the message is sent in plain text without encryption. Eve, who is a malicious hacker, is spying on the communication between Alice and Bob. In this case, Eve can intercept and read all the exchanged messages. To avoid this issue, encryption must be used to hide the data from Eve. Now in scenario 2, Alice decided Now in scenario 2, Alice decided to encrypt her secret message with a shared session key before sending it to Bob. Eve, who is a malicious hacker, is spying on the communication between Alice and Bob. In this case, Eve has intercepted the sent message, but he will need a key to decrypt it and get the original message. Now Bob receives the encrypted message and uses the same session key to decrypt the message and get back the original data. Let us talk now about symmetric encryption. In symmetric encryption, we are using the same key to encrypt and decrypt the data. So to encrypt this plain text into this ciphertext, we will use this key. And again, if we want to decrypt this ciphertext and get back the original data, we will use again the same key. Symmetric encryption algorithms examples include AES and DES. But what is asymmetric encryption? In asymmetric encryption, we are using two keys. The first key is called public key, and we will use it to encrypt the data. The second key is called private key, and we will use it to decrypt the data. So if we want to encrypt this plain text into the ciphertext, we will use the public key. And if we want to decrypt the ciphertext and get back the original data, we will use in this case the private key. Asymmetric encryption algorithms examples include RSA and elliptic curve. Just one thing to mention. This is a public key, that means this will be shared. But this is a private key and will be kept secret because only the owner of this key will use it to decrypt the messages. Now let us talk about hybrid encryption. An hybrid encryption is the combination of both asymmetric encryption and symmetric encryption. Asymmetric encryption is by design slower than symmetric encryption. So to exchange a large amount of data securely, it is better to use symmetric encryption. But in symmetric encryption, same key is used by both parties to encrypt and decrypt the data. But how do we exchange this key in the first place? To exchange securely the symmetric key, we can use asymmetric encryption. Now let us see this in action. Imagine this scenario. Alice wants to communicate with Bob using encryption, and Bob has two keys. One is public, and he is using this key to encrypt data, and another one is private and used to decrypt the data. Bob will send his public key to Alice. Now, Alice generates a random symmetric key called session key. After that, Alice encrypts the session key using Bob's public key. Now Alice sent the encrypted session key to Bob. Bob decrypts the encrypted session key using his private key. In fact, the session key is encrypted using Bob's public key, so it can only be decrypted only by Bob's private key. Now Bob and Alice start communicating by encrypting and decrypting the exchanged data using the shared session key. At the end of the communication, the session key is destroyed, and if they want to communicate again, a new random session key will be created. Hello and welcome. In today's video, we are going to build a Python code that can generate hashes and encode data. First, let us start with the shebang line. User being Python 3. Now we import the needed modules for encoding, and this will be for hashing. We are going to encode and hash the password 1234 plus. Before encoding or hashing any data, first we need to convert it into binary. So UTF-8 password encode UTF-8. Now let us encode the password. B64 password is equal to bin ASCII B2A base 64, and we use this one. And for X we use this. Now let us print the results. Print B64, print X. Now let us check what we have. The first line is in base 64 and in the second line is in hexadecimal. The letter B here means binary, and this is the return of line. So to get rid of this, first we decode data from binary to string, then we use the function strip the same thing for hexadecimal. Let us print the results. Okay, now let us move on into hashing. Hash the password. Hashing algorithms equal MD4, MD5, SHA-1, SHA-224, SHA-3 224, SHA-256, SHA-3 226, SHA-512, SHA-503, 512. Okay. For hashing algorithm, in hashing algorithms, password hash is equal to hashlib new the name of the hashing algorithm to be used, then the password in binary format, then we use the function x digest to get the hash. Now let us print the results. Print password hash. Those are the hashes for our password. I will make the output better. So this is the name of the hashing algorithm. I want to have the same space between this and this. So I will multiply it by 5 minus len of hashing algorithm. Let us check. This is better. I want also to have the hash length in bytes, len of the password hash. We need to divide it by 2 because 1 byte is 2 hexadecimals. This will be a float, so I will convert it back into an integer. Now let us print the results. I will click this, and here we have. So let us make a summary. This is base 64, this is hexadecimal, this is the name of the hashing algorithm, this is the hash, and here the length of the hash. Hello again. Now we will generate hashes for SQL servers. For this we will need the module passlib. So from passlib point hash import MySQL 323 MySQL 41. Now we will move to SQL servers. So MS SQL 2000, MS SQL 2005, 5. Now Postgres MD5, Oracle 10, and Oracle 11. SQL hashing functions, print will start by MySQL. We use the function hash, and now the password in binary format. Let us print the result. Python 3, something is wrong. MS SQL. Okay. MySQL 41. MySQL 2000. MS SQL 2000. MS SQL 2005. 2005. Postgres. Postgres MD5. Oracle 10. And Oracle 11. I will align this to improve the output. Just one thing, those two hashing functions use a username as a salt. So we need also to add the username. So username, I take administrator as an example. This will be converted to byte. Username encode UTF-8. UTF username. So user equal and user equal to this. I will separate native hash functions and SQL hashes by new line. Print n. This is base 64. This is x. Hash the password using native functions. Let's print again the results. Base 64. Okay, now I will add some colors to the output. This will be red color. $31M. Now yellow 33, cyan 36, white will be 0M. This is white, yellow, this is yellow, this is cyan. Cyan, and here the white. I will copy this. Now let us check. This is better. I have something wrong here. Something is wrong. I don't need this. Okay. I will make the same thing also for these hashes. So here password hash, this one, cyan, and this is white. Now let us check again. Okay. Hello again. Now we will add new functionalities in order to make hashes for Windows operating system. In fact, modern versions of Windows have different accounts, including NTLM and MS Cache. NTLM hashes are used for local accounts and MS cache hashes are used for domain accounts. This is stored in C system 32 config security, and this one is stored in C system 32 config some database. Now we import the read module from passlib import lm hash nt hash. Those two will be stored here, and those are the NTLM hashes. This is the old one and this is the new one, and here ms cache and ms dcc 2. Windows lm hash now the empty hash and now the mc cache mc dcc. We need for this the username as a salt. Username ms cache ms cache version 2. Now let us check Python 3. Okay, one thing to mention, this will be installed by default in Python. Native module, also this one, native module, but passlib is a third party module to be installed using pip3 install module install passlib. Welcome to the section hashing using key stretching algorithms. In fact, hashing functions like MD5 and SHA-512 were designed to be fast, and this made them weak against brute force attacks. To resolve this issue, we need to use a very slow hashing function like a key stretching algorithm. First step is generate a random salt and add it to the password. Then starting the hashing process and repeating it many thousands of times until getting the hashing result. Examples of key stretching algorithms include password-based key derivation function 2, SHA-512 crypt, which is used to store user password in etc shadow for Linux operating system, and the Blowfish crypt, which is used for FreeBSD operating system to hash user password and store them in etc master.passwd file. Now let us jump into coding. First we import the needed module from passlib.hash import kdf2 SHA-512 SHA-512 crypt and bcrypt. Now we generate a random salt. Random salt. Salt is equal to random size is 32 byte. 2 byte. Decoded salt is salt being ASCII. The salt decode strip decoded salt you will replace the plus sign with a dot and you will remove the equal sign. Print salt now let us check the result. Python 3 your random is not defined. Okay, from OS import your random. This is our random hash, random salt. Now let us generate the hashes. Derivation function 2. This will be the number of iterations, 100,000. Salt equal salt. Let us print. $512. Now SHA-512 crypt 12 crypt SHA-512 crypt salt is not the same as those two. It is decoded only 16 bytes. By default in Linux operating system, the number of rounds is 5000. Retrieve password, round, salt. This is, where is the salt? This one. Only the first 16 characters of the salt. Until here. Same thing here. Is not defined. $256. Now we go on to bcrypt. BSD crypt is the decoded salt until 21st character. 22 character. BSD salt equal salt. We need to replace the last character by dot. 21 and this is SHA-512 SHA-256 and this is bcrypt. By default it is 12 and this is BSD salt. Let us check now. Did you see that those algorithms take more time than those ones? I will repeat again. I will add another thing to make it more clear. Import time. T1 equal time here. We will print how many seconds it takes to generate the hashes. Print minus T1. Not print. This will be in red. Seconds. Normally like this. T1, T1. Let us check. As you can see, this will take 0.2 seconds. This will take 0.007 seconds. This will take 0.005 seconds. This is 0.07 and this is 0.06. If we increase the number of iterations, the needed time to generate the hash will also increase. Let us check. I will increase this by 13. This will be 6,000. This will be 2. Let us check. We will open another terminal to check the results. Python 3. We start with bcrypt. Now it is taking 0.5 seconds. Before it was 0.2, 0.005, but why normally this also increase around 7,000, 0.005. This has increased 0.06. This is almost the same. I will increase again. So instead of 6,000, I will put 8,000. And here 8,000. This will be let us check now. This will be 14. This is 0.9. It was 0.07 instead of 0.2. Now it has increased to 0.9. So as a conclusion, if we keep increasing the number of rounds, the key stretching algorithm will become more slower and will become more robust to password cracking algorithms. In the last video, we have seen how to generate hashes. Now let us see how we crack those hashes. First thing to do is to generate a word list of passwords. Then we will get those passwords one by one. Then from the hash to be cracked, we will get the salt. Then we will add the salt to the password and generate a new hash. We call this new hash Z. After that, we will make the comparison between the result hash and the hash to be cracked. If both hashes are the same, that means we have found the password. Otherwise, we need to get the new password and repeat again the same process until we find the good password. Now let us jump into coding. First thing to do is include all this code into a new function called password hash. Password hash. We only need one parameter. I will remove this. Then we will import new modules. This to pass parameters from command line to the code. Threading to make our code faster. Queue to generate to store the password in a queue, and sys to use the exit function. I will copy this code. Now I will explain it. Here we are passing parameters from the command line. The first one is the mode. That means it is hashing or cracking mode. If it is hashing mode, we will need also the parameter password to be hashed. If it is cracking mode, we will need the remaining parameters, which is password hash, the hashing algorithm, the word list, the number of thread, and the username salt. And here we are getting the values of those parameters. After that, we call the function main with those values. Now we will define the function main. First thing to do is define a new queue to store the passwords. Then we will create 3 lists of algorithms. This one to be used with the module hashlib, this to be used with the module passlib, this also with the module passlib, but for this we need also a username as a salt. So if the mode is hashing, we will call the function password hash. If it is cracking, we start by calling the queue. Then we will open a word list and get all of its passwords and add it to the queue. After that, we check if we have the word list, otherwise we will see this message. Then we check which hashing algorithm we are using. Then we start a new thread. The new thread will call the function password crack with the parameters password hash, hashing algorithm, the list of the hashing algorithms, and the username salt. Now let us define the function password crack. First thing we check if the queue is not empty, then we get a password. Check which type of hashing algorithm it is using. If it is type 1, we will use this code. Otherwise, this one with cryptotext. Otherwise, this one with cryptotext and the username. Another thing we need to include is this one. Now let us run our code. Python as you can see here are all the parameters that we can use. First, let us check the mode hashing and password 1234 plus. Just one thing to check. Password. Okay. Now we are executing the hashing function. Now let us execute cracking mode. Python 3. We will use MD5. I will crack this. The password hash. The hash algorithm SHA-512. The word list to be used. I will create another word list. I will copy one word list from list. Passwords. I will copy this one. Then I will add this password in the last line plus. $10 million. We need also, we don't need the username as salt. The number of threads I will keep it for the moment as 1. I need to include the mode. I will add the time command. As you can see, in less than 1 second we have found this password. Now if we use this one, ms dcc, msdcc2, this one, msdcc it needs a username. Username will be administrator. It is taking more time now. It has found it at 3 seconds. If I increase the number of threads to 8, it is in 1 second. Now let us check this one. It is SHA-512 crypt. We don't need any username. I will keep the number of threads as 1. Let us check how many times do we need. 3 seconds. Now we will learn how to encrypt and decrypt data using Python and AES encryption. First, we import the needed module. From OS, import your random function to generate random bytes. We will use AES encryption with CFB mode. In fact, we have a lot of modes in AES, and CFB is one of the most secure ones. We will need a key to encrypt and decrypt the data. Its size will be 32 bytes. We will also need an initialization vector, ICIV, and its size is 16 bytes. Now we will generate random bytes using urandom, 32 bytes, and this, the IV, it is 16 byte. Now let us print the key, and this is the IV, Python 3. So this is our key and this is our IV. As you can see, it is in binary bytes. I want to print it in hexadecimal, so I will import bin ASCII module. Now I will call bin ASCII binary to ASCII hexadecimal. This is the key. We need to decode it. This will be the IV. Now let us print the results. This is better. I will include now this code inside a function called AES generate key and IV. Now let us run again our code. Each time we run this code, we get a random key and the random IV. Now let us continue our coding. Now we'll import this module from crypto.cipher import AES. Now we define another function called AES encrypt. This will be the data to be encrypted. This will be the key, and this will be the IV. Our key will be converted from X to binary. So to binary. The same thing for the IV. This will convert X to binary. X string. The same thing for the IV. Now we create a cipher object. We will call it AES cipher is equal to AES this one dot new our key, our IV, and the AES mode. AES dot mode CFP. Here create a cipher object, Now we encrypt the data. So cipher text is equal to AES cipher dot encrypt. We will encrypt this plain text, but first we need to encode it. Now let us print the ciphertext. I will comment this. Now I will call this one. I will use this key, and I will use this IV as an example. And the message to be encrypted will be secret message that must be encrypted. Now let us run our code. So here our message now encrypted. To decrypt our data, this will be decrypt. This will be the ciphertext. here is equal. We need to convert it also to binary. Now the plain text after decryption, this will be plain text, and this dot decrypt. We are going to decrypt. So here we are converting the first thing. We are converting the ciphertext from X to binary. Here we are decrypting. And now we will display plain text. I will use the same key and the same IV decrypt. So this is our message. Let us now check the results. And here again, we have back our secret message that we have already encrypted. Now we will create a main function and include all the code inside it. So def main, the first parameter is mode. If mode is equal to AES generate key IV, in this case we will call this function, and if mode is equal to AES encrypt, in this case we will call this function with those parameters, and if mode is equal to AES decrypt, so we will call AES decrypt with those parameters. We need to add this to the main function, and also the ciphertext, else display invalid mode. And exit. I will comment this. Now if name is equal to main, this module will enable passing parameters from command line. So import arg parse dot argument parser. This will be the description of our code, encryption and decryption using AES encryption. Now we start by adding the needed arguments. Parser, point, add argument. I will delete this. M for the mode. It can only be mode, can only be AES generate key IV or AES encrypt and AES decrypt. Now we add the other options, which is the plain text, this P, plain text, this is help equal help is equal, this is data to be encrypted. Now C is the ciphertext. This is the ciphertext and data to be decrypted. Now we will add the key. So this is AES key. Of size 32 bytes in hexadecimal format. And this is the IV. AES IV of size 16 bytes. Now get the value of these options. Args is equal to parser dot parse args. Now mode equal args dot mode. This is plain text. And this is the ciphertext. Here our key. And here the IV. I will align this equal signs Now we call the function main with those parameters equal mode equal plain text AES key equal the IV, and this is the ciphertext. After that we exit. Let us check our code. We import the needed module. This is the mode. This is the options. Okay, let us now run our code, Python. If we type help, we get all the available options. We will start. I will divide my screen. So the first mode is generate key and IV. Python 3 AES mode. This one. AES key is not defined. S key is not defined. Key and AES IV. Let us check again. So this is our key and this is our IV. If you run again the code, we get another random key and IV. Now let us encrypt some data. AES encrypt. Our key will be this one, and our IV is this one. We will encode password is secret and must not be shared in plain text. So this is our encrypted data. To decrypt it, we need to use the option ciphertext. Now we get this data encrypted. We need to change the mode to decrypt. AES decrypt the key. Something is wrong. Okay, here we have again our secret message, now decrypted. In this lesson, we will see how we can implement asymmetric encryption using Python. First, we start with the needed module. Now we will generate an RSA key of size 2048 bits. So key is equal to RSA dot generate 2048. Now we get the private key, get private key, dot export key. This will be in binary, so we need code to convert it into a text. So decode. Now we print the private key. Same thing for the public. Because in asymmetric encryption, we have two keys. One is private and another one is public. So we get the public one. Private, public. Now we display those keys. So this is the private key and this is the public key. Now we will export those two keys into external files. So we open this file, wt. W means open for write and T means text. Then we copy the private key to the file, to this one. After that, we close the key, we close the file. Now, same thing for the public. Now we check the files. So this is the private key written to this file. Now we check the file public key, which is this one. When we are dealing with asymmetric encryption, we must keep our private key hidden and encrypted. So this private key must be encrypted. For this, we will add those parameters. So passphrase. And here you put the password to encrypt the private key. I will call it just password for private key. And here we will put the type of encryption. As you can see here, now it is encrypted. To display the difference between those keys, I will print the key without encryption. So this is our original private key. Now it is encrypted, and this is the public key. I will delete this one. Now I will include all this code inside the function called RSA generate key. Def RSA key generate the size, key size. And I will put this inside try except, and here what was the issue. Now exit. Now we call the function 2048. Now we have the key encrypted, and this is the public key. Now that we have generated a public and a private key, we will generate a session key and we will encrypt it using RSA public key. This is what we call hybrid encryption. So the first step is generating a random session key. For this, we will need the module OS. So import OS at the first step. Now we will get our session key os.urandom. It will be of size 32 bytes. I will comment this for the moment. Let us print our session key. As you can see, it is a binary object, so it is better if you convert it into hexadecimal ASCII text. We will include bin ASCII module. We use the function binary to ASCII. We want it in hexadecimal, so X. It is a binary, so we need to decode it. Dot decode. Now we print the session key. Now it is in hexadecimal format. The next step is creating a cipher object and encrypt the session key using our public key. So first get public key is equal to RSA. We use the function import key. Here we will open the file public key and we will read its data. Now we construct a cipher object. RSA cipher object. So RSA cipher public key CS1 or AP.new, and we use the public key. So from crypto.cipher we will import this class. Now we encrypt the session key. Is equal to RSA object dot encrypt the session key. Now we display the encrypted session key. It is a binary object, so we will display it as an hexadecimal, just like this. Now we display what the results. Binary to X is not defined. Bin ASCII. So now this is our session key, and here it is encrypted using RSA public key. If we run again the code, we will get again another session key. Here again another session key, and here it is encrypted. Now we will take an encrypted session key and we decrypt it using our private key. First thing to do, I will include all this code inside a function called RSA session key encrypt. So define RSA session key encrypt, and I will include also a try except statement. In case we have any issue, it will be displayed here. And then we exit. Next, we will call our function. We need only the public key file name, public key file, RSA encrypt, and encrypt the session key. Now let us run our code. Python 3 RSA. So here we have a random session key, and here it is encrypted using our RSA public key. Now we will decrypt this key using RSA private key. So I will command this and I will copy all this code. This will be decrypt. This will be private key file. Private key file, that means this one. Now encrypted session key. I will take this hexadecimal string we need to convert it from hexadecimal into binary before decrypting this key. So encrypted session key is equal to and here ASCII to binary, and before that it must be encoded. Dot encode encrypted session key from ASCII to binary, and here it is encoded. Now we get the private key. Our private key is protected by a password, so we need to include this parameter also. Otherwise, we will not be able to open the file. Import key open private key file, read here private key and decrypt. Now the session key, decrypt, encrypted session key, print decrypted session key, binary to hexadecimal. Now let us run our code, and here we have again our session key. So first we have generated a session key. It was encrypted using our public key, and then from this string, the encrypted session key, we get back our session key using the private key.